In today's lecture, we are going to start a very important chapter of quantum mechanics, and this is actually the theory of scattering. Actually, theory of scattering is an important chapter of quantum mechanics. You have also learned about this scattering problem in classical mechanics. You can see the playlist of classical mechanics of my channel. I have provided so many lectures on theory of scattering. But there you will find the theory of scattering by classical approach. But this chapter which we will see from today, that is meant for the fulfillment of quantum mechanical approach of theory of scattering. It is very useful for the students of B.Sc level, M.Sc level, and also for NET JRF examination and several other competitive examinations. So this is a very important chapter, and as I hope you will see all the videos provided by me on this in this chapter, and definitely that will fulfill your requirement for your examination purpose. Actually, when you talk about the scattering theory in quantum mechanics, then you can see that experiments on scattering provide one of the most important means of gathering information in the realm of atomic and subatomic particles. When you talk about scattering in classical mechanics, that scattering is not confined to atomic and subatomic particles. But whenever you are talking about the theory of scattering in quantum mechanics, that actually gives you informations about the atomic and subatomic particles. So it was, you have definitely studied earlier in my video too, that it was Rutherford's experiments on scattering of alpha particles that provided the experimental basis for the nuclear atom model that eventually led the Bohr atom model and to quantum mechanics. Okay. So the scattering theory starts from the Rutherford scattering experiment, which was performed by Rutherford and his students Geiger and Muller. And you have seen that when an energetic beam of alpha particle strikes a thin gold foil, then most of the alpha particles pass through the gold foil undeviated, but some of them deviates by a large angle. And from that experimental result, Rutherford concluded that the total mass and charge of the atom is concentrated in a very small volume, which is nowadays called nucleus. So this was a very fantastic experiment, and you have learned about this Rutherford scattering in classical mechanics by classical approach. But in this chapter, you will again learn this, but by quantum mechanical approach. Okay. Actually, in nuclear physics, I have also provided so many lectures on this scattering problem, like NP scattering, NN scattering. You have studied. Okay. Actually, many of the features of the nuclear force, such as its range, strength, and spin dependence, have been deduced from the data gathered from Nucleon-Nucleon scattering, which we have already learned in my videos in nuclear physics in the chapter nuclear force. Okay. In fact, a scattering of electrons from nuclei as well as nucleons has helped in determining the charge distribution in the later. Okay. In fact, the importance of the role of the scattering experiment as a peep-hole into the world of nuclear and subnuclear particles cannot be overemphasized. Okay. Actually, in this chapter, we propose to present some aspects. When you say some aspects, because when this scattering problem will be dealt in very detail, then there will be a completion of a book. Okay. You can see several books on this scattering theory, like Goldberger and Watson book Collision Theory. Okay. Similarly, R.G. Newton books Scattering Theory of Waves and Particles. These are actually a complete book on this theory. So we cannot claim that we will learn everything about the collision of particle and waves or scattering of particle and waves in this chapter, but our aim is to give some important aspects in accordance with our syllabus. So I am telling you that we propose to present some aspects of the quantum theory of scattering in this series of videos. Okay. And after describing the scattering experiment and the quantities measured in the experiment, we will consider two different methods of scattering. And one is suitable for low energy scattering, okay, and the another is meant for the high energy scattering. Actually, what we will learn in this scattering problem, the most important parameter from which we gather the information, that important parameter or experimental quantity which gives you the idea of the scattering, the concept of the scattering, and the nature and features of the scattering, that is actually called a scattering cross section. In terms of a scattering cross section, we gather each and every aspect, each and every feature of the scattering. Okay. And when you say scattering cross section, then you will see there are two scattering cross sections. One is called differential scattering cross section and another is called total scattering cross section. Okay. So actually, if your plan is to deal with the problem of quantum mechanical theory of a scattering or classical theory of a scattering, first of all you must have an idea of this differential scattering cross section and the total scattering cross section. Okay. In fact, differential and the total scattering cross section could be regarded as the experimental quantities of the scattering problem. Okay. The aim of a scattering theory is then to use these to deduce information on the force or the interaction responsible for the scattering. Okay. So in this first lecture on this theory of scattering in quantum mechanics, I will provide you just a brief idea or of this differential scattering cross section and the total scattering cross section. And after that, in the next consequent lecture, we will see if your aim is to discuss the problem of a scattering by quantum mechanical approach, definitely you have to relate this scattering cross section with the wave function of the system. So how this scattering cross section is related to wave function, that we will learn in the forthcoming lecture. Okay. For clarity, I am going to discuss only the definition of differential scattering cross section and the total scattering cross section in this lecture. Okay, because these are the most important and most useful experimental quantities to discuss the problem of scattering. Okay. So now let us see how we can develop the concept of differential scattering cross section and the total scattering cross section. Actually, whenever you talk about a scattering, definitely there should be an experimental arrangement. In this figure, schematically, I have shown a very simplified version of an experimental arrangement for any scattering problem. Definitely, when you talk about a scattering experiment, actually there are three important parts of this experiment. First of all, you must have a target on which we will strike a beam of particles, okay? And then the beam of particles get scattered from the target, and the scattered particles must be detected. So there must be a detector. So actually there are three important parts. First one, as you can see, there should be a beam of incident particles. Then there should be a target, and this is a detector. This is detector, which will detect the scattered particle. Okay. So you can say that in a typical scattering experiment, a beam of homogeneous monoenergetic particles, when you say homogeneous monoenergetic particles, that means an ensemble of particles. Okay. Monoenergetic means each and every particle must have same energy. So such a beam of homogeneous and monoenergetic particle falls on a target, as you can see here. Okay, this is a target. And when you say target, in general, this target is in the form of thin foil. As you know, in the Rutherford alpha scattering experiment, he has taken a thin gold foil. So the target is in general in the form of a thin foil. And this target actually consists of a large number of scattering centers. What are these scattering centers? We will learn in our further lectures. That may be nucleus, okay? And that may be any atom, that may be a molecule, okay? Actually, those atoms, those particles or nuclei are responsible for scattering, so they are collectively called scattering centers. Okay. So when this homogeneous monoenergetic particles beam is incident on the target, that is the thin foil, then due to the scattering center there is an interaction between the incident particle and the scattering center of the target. And during this scattering, you know, a very strong force, impulsive force acts on the striking beam, by virtue of which these particles get scattered almost in all directions. Although some of the particles, of course, proceed along the incident direction unaffected by the target. Okay. And these scattered particles must be detected. So we need a detector to detect the particle. So you can see in this figure that the particles are scattered by the target in all directions, and the scattered particles are received and analyzed by a detector as I have shown here. Actually, this detector is placed at a very large distance from the target or the scattering center. As I have shown in this figure, that this detector is placed at a distance r from the target. When you say that the detector is at a large distance from the target, what does it mean? This distance is just relative. Actually, this r must be very large in comparison to the dimension of the target. Okay? Dimension of the target. Compared with the linear dimension of the target, this distance r must be very large. This is an experimental requirement. Okay? So if target is let us say very thin, it is of thickness, let us say 10 to the power 0.1 mm, let us say. Then if the detector is situated at 50 centimeter, that is very large distance, because you have to compare the 50 centimeter distance with 0.1 millimeter. Okay, so actually we can say that this detector is situated at a large distance compared with the linear dimension of the target. Okay, as you can see in this figure that we have actually considered a coordinate system here, and the origin of the coordinate system is considered or taken at the target. Okay, and I have considered that the incident beam or the striking beam is actually when it is just a striking, when it has not suffered a scattering, that is the incidence direction is along the z-axis. We have considered it. Okay, so this is the basic experimental arrangement. We need a target which is a thin foil. We need a detector which detects the scattered particles, and we need an incident beam of particles which strike the target. Okay. Now, as I have told you that this short lecture is only meant for knowing the definition of differential scattering cross section and the total scattering cross section. Why we need it, I have told you already that this is the experimental quantity in terms of which we will learn in our forthcoming videos, that we can get informations regarding the interaction taking place between the scattering center and the incident particle in terms of this differential scattering cross section and total scattering cross section, when we will relate these two with the wave function of the system. So now let us try to know what are these differential scattering cross section and the total scattering cross section. Actually, what I have explained, I have actually mentioned here, I have written for your convenience. So I will suggest you can note down these things in your notebook so that it will be very helpful for your examination purpose. Okay. Now, for knowing the idea of differential scattering cross section and the total scattering cross section, let us consider that this d omega, which actually I have shown here, you can see this is the solid angle d omega. And you know this d omega is the solid angle subtended by the detector at the target. Okay. And how this d omega is defined? You know, solid angle is defined as ds divided by r square, where ds is this elementary area, you can say this is ds, and r is its distance from this center. But in a spherical polar coordinate system, you know that this elementary area ds is given as r square times sine theta d theta d phi. This is the expression for the this surface area element in a spherical polar coordinate system. So this r square and this r square will cancel out, and you can say that this solid angle subtended by the detector at the target is simply equal to sine theta d theta d phi. Okay. And we have also assumed that this omega which is just the angle which actually measures the angular position of the detector. Omega, this is capital omega, which measures the angular position of the detector, and this angular position, when you say omega, that is actually a function of theta and phi. So instead of both theta and phi, you can write omega. So with the incident direction how this detector is, where this detector is oriented, situated, that can be measured in terms of this omega. Okay. And after that we consider that this what dn. Actually we consider that this dn is the number of particles received by the detector per unit time. How many particles strike the detector, okay, or how many particles are actually received by the detector in unit time, that is equal to dn I have assumed. Okay. So dn is the number of particles received by the detector per unit time. Okay. And we also consider that this J naught, this is the number of particles crossing unit area perpendicular to the direction of beam per unit time. This is actually called the incident flux. If you consider, let us say this is an area on which this incident particles strike normally. Okay. Then through unit area of this surface, how many particles passage in unit time. Okay. If you consider that the total number of particle is n, which strikes on the area, let us say S, in time t. Okay. So you can say that in time t on through area S, the total number of particle passing is n. So in unit time through unit area, how many particle will pass? This will be n divided by S into t. Actually this n divided by S into t, that has been denoted by the symbol J0. Okay. That is denoted by the symbol J0. Okay. And this is called the incident flux. Okay. So remember, this J naught represents the number of particles passing through unit area of a surface kept normal to the incident direction of the beam in unit time. Okay. And we also consider that this small n represents the number of scattering centers in the target. Remember. So all these quantities I have assumed. Actually, this dn, you know what is this dn? Dn is the number of particles received by the detector in unit time. Actually, this dn will be proportional to n. If the number of scattering center is large, then the number of scattered you can also say that this is actually the number of scattered particles in the direction omega, because the detector is oriented in direction omega from the incident direction. So you can also say that dn represents the number of scattered particles, okay, scattered particles in direction omega. Okay. This, as the number of scattering center will be large, it is obvious the number of scattered particle will be also large. Again, J naught actually represents the number of striking particles per unit area per unit time. So if you will strike larger number of particle in unit time on unit area, definitely the scattered particles number will be also large. So we can think that this dn should be proportional to modulus of this J naught. Okay. And again, if d omega is large, if we consider particles going through larger solid angle, definitely number will be larger. So these are obvious that dn is proportional to n, it is proportional to mod of J naught, and it is proportional to d omega. Or you can say that dn is proportional to n times mod of J naught times d omega. But this relation does not hold always. You will see that there are two conditions. When those two conditions will get satisfied, only then you can say that dn is proportional to n times modulus of J naught times d omega. Okay. And what are actually those conditions when this relation will hold? The first one is the intensity of the incident beam is low enough for the mutual interaction among the particles to be neglected. When you say the intensity, what does it mean? Intensity means the density or the number of particles per unit volume. Number of particles per unit volume. Let us suppose there are large number of particles in unit volume. Then definitely there will be some interaction between the particles due to the larger density, because particles will be then very close to one another and we cannot neglect the mutual interaction. But in this experiment, we have to assume that the incident particles do not interact with one another. So when they will not interact with one another? Only when they are actually far separated. And they will be far separated only when their density is small, number is small. So for the validity of this relation, the first condition is the number of particles per unit volume, or the density of particles, or you can say intensity of the incident beam, must be low enough. And when this will be low, then you can easily neglect the mutual interaction among the particles. Okay. So this is the first condition. So in nutshell, you can say for the validity of this relation, the intensity of the incident beam must be very low. Only then this relation will hold. Now, the another important condition which must be satisfied for the validity of this relation is the momentum P of the particles is large enough so that de Broglie wavelength, which you know is given by h by p, is small enough. If p is large, then from this de Broglie relation you can say that this de Broglie wavelength will be very small. Okay. And if de Broglie wavelength will be very small, then the scattering centers act independently of each other in the scattering of particles. It means in this condition, each and every scattering center will be unaffected from the presence of other. And this is another requirement for this scattering experiment. So for the fulfillment of the independence of a scattering center from each other, the de Broglie wavelength must be very small. And for a smaller value of de Broglie wavelength, you know, the momentum of the particle must be very large. So when actually these two conditions will get satisfied simultaneously, only then you can say that dn is proportional to n times mod of J naught times d omega. Only then. But we have told this fact very in a simple manner, but satisfying these conditions is not an entirely painless affair. This is a tough affair. This is a very painful affair. These conditions do not get satisfied very easily, because when you talk about the condition number 1, that is intensity of the incident beam should be very low. Actually, this condition 1 conflicts with the requirement of good statistics, which favors a large intensity, the larger number of counts at the detector during a given time. Okay, the better the statistics. Okay. Similarly, if P becomes too large, which we have told in this second condition, if P is very large, then phenomena more complicated than simple scattering such as particle production will begin to appear, We will learn about pair production in our forthcoming lectures. Okay. So there are optimum values of J naught and P for a given setup. You can't take P very large, you have to take an optimum value. Okay. Similarly, you can't take this J naught very large, very small. You have to take an optimum value. So, in a particular experimental setup, these two conditions are not strictly followed, and therefore we have to choose an intermediate path. And in that intermediate path, we have to select an optimum value of J naught, that is this intensity, and the momentum P. Okay. But for a time being, let us consider that these conditions hold good, and then we can write that dn is proportional to this much. But you know, when we will remove this sign of proportionality, there must be a constant factor. So after removing the proportionality sign, you can write that dn is equal to sigma of omega times n times j naught times d omega. Here, sigma of omega, this is the proportionality factor, or you can say proportionality constant. Okay. Now actually this sigma of omega, you will see, has the units and dimensions of area. How you can say that its units and dimension will be that of area? You can see sigma of omega, this will be equal to, from this equation 1, dn divided by n times mod of j naught times d omega. Dn, you know, this is just the number, okay, of scattered particles per second. See the meaning of dn. dn is what? dn is number of particles received by the detector per unit time. So its unit will be 1 over second, that is second inverse. Okay. N is simply the total number of a scattering center. So this is a number, you see, it is dimensionless and unitless. So n has no unit. And J naught, this is actually the number of particles passing through unit area in unit time. And you have seen that this J naught is equal to this much. This is n divided by s time t. N is number, so it is unitless. So this is 1 over, and unit of s is meter square, and unit of t is second. So its unit will be meter inverse to second inverse. Okay. So the unit of this J naught is meter inverse to second inverse. And d omega, this is solid angle. This is dimensionless, you know. This is dimensionless. So this second inverse and second inverse will cancel, and its unit or dimension will be meter square, or you can say L square. But you know that L square or meter square is the dimension of area. So I have told you that this proportionality factor sigma of omega, actually the value of sigma will depend on this omega. So I have written sigma as a function of omega. Its dimension, you can see easily that it is the same as that of area. Actually this quantity sigma omega is known as differential scattering cross section. This is differential scattering cross section. We will define it sometime later, you will see. Okay. So I have mentioned here that you can see that the proportionality factor sigma of omega has the unit and dimension of area. Okay. And that's why this is called cross section. Why the word cross section? Now you can learn. Okay. Now let us consider that this Js of omega be the scattered flux. It means this is the number of particles scattered in the direction omega per unit time, per unit time, per unit time through unit area. Unit number of particles scattered in unit time through unit area in the direction omega. This is Js omega. So this is called a scattered flux of the particle in the direction omega. Now, since this is the number of particles passing through unit area in unit time in direction omega, so the dn can be expressed in terms of this. dn can be given as modulus of this Js times r squared times d omega. Okay. Here r, is the distance of the detector from the target, as you have seen in the figure. Now, you can see in equation 1 we have defined this dn, and here too we have also defined this dn. How dn has been defined in this equation 2? You can see. Since you know d omega is equal to what? This is ds by r square. Okay. So what will be this ds? ds will be equal to r square times d omega. Okay. And Js, it is number of particles scattered in unit time through unit area. Mark it, through unit area. So through unit area, the number of particles scattered in direction omega is equal to Js, is equal to Js. So what will be the number of particles scattered in unit time through area ds? Then you have to multiply this by ds. So dn will be equal to mod of Js times ds, but ds is equal to r square d omega. Okay. So I have written this dn equal to mod of Js times r square d omega. I think you have clearly now understand how we can write dn equal to mod of Js times r square d omega. Now we have defined this dn in equation 1 and 2 both. Okay. So we can now easily equate these two values of dn. Okay. So let us see. We can write sigma of omega times n times mod of j naught times d omega is equal to mod of Js times r square d omega. And therefore, this sigma of omega will be equal to this much, because this d omega and this d omega will cancel out. So this is actually the defining equation of this quantity sigma of omega, which I have told you that this is actually called the differential scattering cross section. This sigma of omega is called what? This is differential scattering cross section. Okay. And it is also obvious from here, if I would ask you what will be the dimension of this sigma of omega on the basis of this equation 3. You can easily say. You can see dimension of r square will be L square. Okay. And n is a number, so it is dimensionless. And dimension of Js and dimension of J naught will cancel out. So finally, the dimension of sigma will be simply L square. Okay. So this result proves our earlier statement that this quantity sigma of omega has the dimension of area. Okay. Now, as you can see, this equation 1. Actually, this equation 1 shows that this sigma of omega is numerically equal to the cross-sectional area of the incident beam that is traversed by as many particles as are scattered per scattering center into a unit solid angle in the direction of omega. From here you can see J naught, you know, this is the number of particles passing through unit area in unit time, okay, and d omega is the solid angle, and when you divide this dn by this much, then you can say that this sigma omega is equal to the cross sectional area of the incident beam that is traversed by as many particles as is scattered per scattering center into a unit solid angle in the direction omega. Okay, so I have written this definition here, that it is clear from equation 1 that this sigma omega is numerically equal to the cross sectional area of the incident beam that is traversed by as many particles as is scattered per scattering center into a solid angle, into a unit solid angle in the direction of omega. Okay. Actually, in general, this sigma of omega, which is called differential scattering cross section, that is denoted by the symbol d sigma by d omega for convenience. So in our forthcoming lectures, when we will talk about the differential scattering cross section, we will prefer to write the symbol d sigma by d omega for it. Okay. So from equation 3, now you can say that this sigma of omega is just equivalent to d sigma by d omega, okay, and that is equal to this much, which I have mentioned in equation 3. Okay. Actually, this symbol d sigma by d omega for differential scattering cross section will be more convincing when we will talk about the total scattering cross section. When we will integrate this d sigma by d omega for the entire range of solid angle, we will get the total scattering cross section. Okay. So after getting the idea of differential scattering cross section, now you can see what is this total scattering cross section. It is obvious from its name that this when you talk about total scattering cross section, that will be simply the integral of differential scattering cross section sigma of omega or d sigma by d omega over the solid angles. Okay. So so the total scattering cross section you can write by the symbol sigma or sigma total, and that is simply equal to integral of sigma of omega d omega, or instead of sigma of omega you can also see that this is d sigma by d omega, and it is obvious from it that this integral will be sigma. So you can say that the total scattering cross section is the cross sectional area of the incident beam that is traversed as many particles as are scattered in all directions by each scattering center, all directions. Okay. So in this way we have defined the differential scattering cross section and the total scattering cross section. This is just a basic definition. But our problem of scattering will be solved when we will learn the relation between the wave function of the system and these scattering cross sections. Then our scattering problem will be solved quantum mechanically, which we will discuss in our forthcoming lecture. Okay. Now we will see some of the important facts regarding these scattering cross sections. Actually, as I have told you earlier, that the differential and the total scattering cross section are the experimental quantities of the scattering problem. I have told you earlier. Okay. And actually in terms of these we get the information about the force which is responsible for the scattering. Actually I have told you this fact earlier. Actually the aim of the scattering theory is to make use of these differential scattering cross section and total scattering cross section to deduce information on the force or the interaction responsible for the scattering. Okay. Actually the theory achieves this aim by establishing a relationship between the cross section and the wave function of the system. Okay, as I have told you earlier. For the wave function, is obtained by solving the Schrodinger equation, which involves the interaction. Okay. So, whereas in bond state problem, the emphasis is on the energy eigenvalues. You have discussed in this playlist of quantum mechanics of my channel so many bond state problem like particle in a box, and in those problems which are called bond state problem, our prime aim is to find the energy eigenvalue of the particle or the system. So I have told you, I am telling you that in a bond state problem, the emphasis is on the energy eigenvalue. But on the other hand, in the scattering problem, the interest centers on the wave function. Okay. Here our prime aim will be to find the wave functions. Also in bond state problem, we deal with a negative part of the energy spectrum. Okay, but when you talk about a scattering problem, it is positive part of the spectrum that comes into play. Okay, so this is a very brief introduction or very brief idea of differential scattering cross section and total scattering cross section, which will be needed for the development of the theory of scattering. Okay, and as I have told you, in our forthcoming lecture we will see the relationship of the scattering cross section to the wave function, where we will talk about a scattering amplitude, and that idea will be utilized directly in the theory of scattering, which we will learn in this playlist, in this chapter. Okay, so I hope you have clearly understand this basic idea and watch the video seriously. Definitely this will be very helpful to you. Thank you very much.